Here are the, we're going to go over the review. Let me list the topics that will be on the exam. So here are the topics. Let's just keep quiet since we're recording this. So there's a signal vector space. Then Gram-Schmidt orthogonalization. Third topic, one-dimensional signaling. That's essentially pulse amplitude modulation. Two-dimensional signaling. That's both QAM and PSK. Correlating receiver meshed filter. Probability of error, waterfall curves. Seven, first Nyquist criterion for ISI-free transmission. So Nyquist criterion for ISI-free transmission. And part 8, concepts in probability. Okay. So I have a whole bunch of problems here. There were also some problems during the office hours that people asked me that we thought we should review in the class. So which one do you suggest we go first? Office hour problem. So let's, where is the?
7.19.
7 point, do you have that book? Okay. 7.19. And there are a whole bunch of other problems that are essentially the same as this one, just slightly different signal waveforms. So 7.19. There are three message signals, M1, M2, and M3. So M1, M2, and M3. And they are to be transmitted over AWGN with the noise power spectral density, so PSD of noise is N0 over 2. The messages are S1 of t is equal to 1 between 0 and this, if there's a typo here. You see that it's not 1, it should be t. Otherwise, and there are two other signals, S2 of t is equal to minus S3 of t, and this is equal to 1 when t is between 0 and t over 2, and minus 1 t over 2. And 0 otherwise. And so then we have a whole bunch of questions. When it comes to these kind of problems, it's always good to draw these signals so that you know what you're talking about. As a matter of fact, don't even start before you draw the signal. So see, the signaling is obviously between 0 and t. Try to do this better. So you start 0. How does S1 of t look like? It's just this, right? So that's S1 of t. S2 of t, this is t. S2 of t is 1 between 0 and t over 2, and minus 1 in here. So this is S2 of t. And then S3 of t is minus S2 of t. So it is, this is again t, this is t over 2. So it's like this, S2 of t. The first question is, what is the dimensionality of this signal space? What is n in this case? Well, you should see right away that S1 and S2 are orthogonal, right? So it's at least 2. And then this is S3, sorry. And then S3 is already given as minus S2, so S3 can be expressed in terms of S2. So the dimensionality here is 2. M is equal to 3. The second question is, find appropriate basis vectors for the signal space. And it says, hint, you can do that without Gram-Schmidt orthogonalization. What you need to remember, the basis vectors are made to be unit norm. Right, so what is psi 1 of t? I'm going to say that this is 1 over energy of 1 times S1 of t. What is the energy of this guy? Well, if I square it and I integrate it, this is t. So, 1 over square root of energy. So psi 1 is going to be 1 over square root of t times S1 of t. So how does psi 1 look like? It looks like this. T, 1 over square root of t. Psi 1 of t. What is the energy of psi 1 of t?
1.
What is the norm of this one? Square root of energy. Energy is 1, so the norm is 1. Now, psi 2 of t, I'm going to say that this is 1 over square root of energy 2 times S2 of t. You cannot say this always, right? This is a special case because I have that S1 and S2 are orthogonal. So the projection of S2 on a direction of S1 is equal to 0. So even if I did Gram-Schmidt orthogonalization, I would get this result here. So again, if I square this one and integrate, this is t, so this is 1 over square root of t, S2 of t. So psi 2 of t looks like this. T is like this, where this is 1 over square root of t minus 1 over square root of t, psi 2 of t. So those are my two basis vectors. The part 3, draw the signal constellation for this problem. Well, this is psi 1, psi 2, go ahead.
It's a 1 over square root of 2t or t?
T, right? Because when you square it,
No, it's 2. You give it to t.
Here, 1 over square root. So where are the constellation points? S1 I get by multiplying psi 1 by what? Square root of t. So S1 is here, square root of t. S2 is essentially square root of t times psi 2, right? So this is S2, or I should call them as they're called over there, M1, M2, and this is M3. And this is square root of t, 0. This one here is 0 plus square root of t. And this one here is 0 minus square root of t. So those are the three symbols in my constellation. The third one, sketch the optimal decision region for this one. Well, if the signals are, and I assume that they're not saying it, but assuming that all of these are equiprobable, so how would I put the decision boundary? Well, I'm going to make it like this. When these have also a fancy name. These are called, maybe you've heard it, Voronoi regions, right? Voronoi regions, if you have multiple points in space, then you look at the adjacent ones and then you draw the line so that you're in the middle between them. And this is how you would create these boundaries. They are, since the symbols are equiprobable, there is no way to, there's no reason to shift the boundary in one way or the other. If I'm deciding between these two, the boundary should be in between them. And so is the boundary for these two and these two taken together. Now the next one is, which of the three messages is more vulnerable to errors than the other ones? So which one is the most likely to make it? We're most likely to make an error. N1. Why is that? Because the boundary is the tightest. So under the same noise clouds, you're going to the most quickly exit from this region than from the other two regions. Right? So N1 is the one that is.
Excuse me, sir. The question says derive the decision boundaries and then sketch it. So what does derive mean?
Well, derive means,
Mathematically?
Yeah, you're going to say something like this. Decision boundaries, I'm going to make the decision based on how close the received signal point is to the constellation symbol. And then somehow you would translate this into mathematical terms. I don't know what the...
Correlate?
Oh, well...
Half the Euclidean distance.
Yeah,
yeah.
Look at Euclidean distance or dot product or whatever. But I thought he wants us to calculate the probability of error, and I don't see that in this problem.
No, it's not.
Huh?
No, he doesn't ask for it.
Doesn't ask for it, but it asks in all the other problems. So let me actually calculate the probability of error. How would you calculate probability of error in this situation? Now, so let's say what will happen when you present one of these signals to a matched filter. What happens at the output? You're gonna have I guess let me actually do that. Let's actually calculate the probability of error when I'm sending M1. Right? So probability of error given M1. So what happens here? I'm going to get a constellation point here, I guess the output of the filter. Is going to be, let's say, Y1 is going to be square root of t plus N1 and 2, right? So I'm going to take the signal and project it along these two axes. If the noise, I have two noises. One is noise along the psi 2, and the other one is noise along the psi 1. Along the psi 1, I have the noise that's offset by the energy of the symbol. So I should really be, if the noise on the N1 is small, I should really fall right into the point, right? But I'm going to be offset by this N1, which is a random variable. What do I know about N1? N1 is the normally distributed with 0 mean and sigma squared equal to N0 over 2. How about N2? It's going to be 0 mean with sigma squared also N0 over 2. So I'm going to be placed somewhere on this, or around this vertical, and I'm going to be offset this direction by n1, and I'm going to be offset by this direction in by n2. So if you were to base this by Euclidean distance, how do we calculate the probability of error? We said probability of error given m1 is going to be 1, or I should say integral over complement of a decision boundary for the 1 of PDF of R given n1 beyond. Right? So that's the how we calculate this. Or I can say that this is 1 minus R1 PDF of R given n1 beyond. Right? So that's what I need to calculate. Now, what does the PDF of R looks like when I'm sending n1? PDF of R becomes, since these two noises are independent of each other, it's product of their two marginal PDFs. So I have 1 over square root of pi n0 e to the minus n2 squared over just n0 times 1 over square root of pi n0 e to the minus n1, sorry, I can say what would be the best one to use? I can say n2 plus square root of t squared over n0, right? The product of the two. If you look at what this is that bell curve, right? That bell, not curve, bell, just a bell, right? It's centered around this area. Take this point out of the board and make it like a bell, right? And it is normal in this direction, so this is this distribution relative to n2. And it's also normal in this direction, but it's centered around the square root of t, so that means I need to put minus here.
Is one of those
Is that
N1
N1?
also?
Hmm?
Is one of them N1?
This one
It should be M1.
Right, because when you plot this one is centered around square root of t, and it has the variance of n0 over 2. And this one is centered around 0, and it has the variance of also n0 over 2. Now, the integral over R1 of this becomes of, let's say, PDF of R given, this is given M1. Becomes an integral, it's a double integral, right? And this is 1 over square root of pi n0, quantity squared, e to the minus n2 squared over n0 times e to the minus n1 minus square root of t squared over n0 dn1 dn2. Okay? And then let's say we need to now decide the boundary. So let's say n1 goes from 0 to plus infinity, and n2 goes from where? So what is the equation of this line? N2 is equal to what? Minus N1, right? So from minus N1 to N1. So I have to go from minus N1 to N. Okay? So that's essentially what we need to evaluate. Any questions here? Do you understand what I'm doing?
Not really.
Is a short.
Can you explain the limits again?
Hmm?
Can you explain the limits again?
Yeah. Let's, this is, let me just draw another picture here. I have these two lines, right? Let's call this N1, N2. What is this one line? N2 is equal function of N1, right? What is that function? They're the same, right? This is the 45 degrees, because this is square root of t and this is square root of t, right? So this line here is N2 equals N1. Do you see that? Okay, so this is N2 equal N1. How about this one? N2 is equal to minus N1, right? So I need to integrate over this area. How do I integrate over this area? N1 goes from 0 to infinity, N2 goes from minus N1 to N1. Right? So this is what I have here. Right? All right, so now it's a matter of how skillful you are in these integrals, right? You know, this is a little bit of the whiteboard problem. If I were to do this, I'll probably move this into polar coordinates, right? And what that would mean is I would introduce substitution. Rho is equal to square root of N1 squared plus N2 squared. And then phi is equal to arctangent of N2 over N1. Right? And what you find out here is that you have, it's very similar actually to the problem derivation I did for the PSK. Right? Because this is kind of like PSK. If you look at this point, the probability of error here is the same as, you know, if you get QPSK, right? So you end up with the same result, and it will take a little bit of time to do that. Right? Okay. Now that's one way of doing it. If I remember, you know, looking at, you showed me the solution manual. He's doing it different, and he's using. So this is how one way of doing it. It's really just following the
Solution manual?
No, this is what following how I derived it for the PSK. If you look at what he's doing in a solution manual, he's using a different kind of metric. Here's the reasoning, and let's just go through it, make sure that it's sound. You know, let's double check, because a lot of these solution manuals are done by students. So it's always
Wrong.
no. It's always needs to be double checked. So let's see here. Probability. Here's what he said. Probability of error, given that N1 is same, is going to be equal to probability that R minus M1 squared greater than R minus M2 squared given M1 plus probability of R minus M1 squared greater than r minus m3 squared given that m1 is 10. So here's the reasoning here. He's saying, when do I make mistakes? I send m1 and the distance to m2 is smaller than the distance to m1. Or I send m1 and I'm somehow closer to m3. Either one of these events will give me erroneous solution, right? Erroneous interpretation. So let's calculate. So now the question that this is why I'm double checking this, because you showed me this, and then is there a case we can do this together where where these two are not mutually exclusive, right? Where you are simultaneously closer than to both M1, M2 and M3 when I'm sending M1, because this would only work if these two are exclusive. And I see that that's the case, right? Because here's, in this region here, I'm closer to, how should I say, this is M1, this is M2, this is M3. So in this region here, I'm closer to M2 than what I'm in M1, right? Everywhere here, to the right, to the up, I'm closer to M2. So probability of being closer to M2 than to M1 covers this entire region here, right? Wherever I fall within this region, I'm going to be closer to M2.
I think it's from the negative N1 to the line instead of the straight.
No. Look at this event. Where am I closer to M2 than M1?
Oh, yeah.
Everywhere above this line, I'm closer to M2 than I'm on M1. Then if I look at this line, everywhere, so this, how do I even draw this? This area here, this way, that's your P1, this guy here, P1, probability 1. Let's call this probability P2. P2 is, I'm closer to M3 than I am to M1. Where does this happen? Everywhere here. So this is P2. So if you now look at, there is a significant overlap where these two are, so I have to subtract this, right? And I don't think he does that in solution.
No.
So the solution is not correct.
So
Yeah.
it's correct.
Because you have to subtract this region because he's double booking in the solution. So I guess you have to go this way. Otherwise you have to modify this solution to match. Yeah. Yeah, I'll think about it a little more, but I'm almost positive that this is not proper way of doing it, because he's double booking this region.
Yeah.
This one here. This needs to be subtracted. That region.
So that.
And also 722.
722. Let's take a look at that.
Wait, excuse me, Professor. So the correct answer is the one with the integral of the integral of the PDF.
Correct answer is you have to crank this integral. This is what you need to do.
But it's not final, right? It's not done yet.
What do you mean it's not done?
I mean, like.
No, you would have to do some work. And if you look at the lecture notes, I actually do this work. I do this work. It's actually solved. And I just and it goes like this. You substitute the polar coordinates, then what happens, they separate into two integrals. Integral over phi is trivial, and then for integral over rho, you solve that. So it's actually given in the notes, the actual solution for this one. 722. Okay, so we have a similar kind of problem. In an additive white noise channel, the noise power spectral density is N0 over 2. This is of noise. We have two signals. S1 of t is given as AT over t for 0 smaller than t smaller than t, 0 otherwise. And the S2 of t is equal to A1 minus t over t, 0, 0 smaller than t, smaller than capital T, 0 otherwise. So it says, determine the structure of the optimal receiver, determine the probability of error. Well, this, again, we sketch this S1 of t. This is how S1 of t looks like. This is A, and this is t. S2 of t A1 minus t over t. So that's the S2 of t. Now these two are triangular pulses. What is an interesting thing here, the S1 and S2 are matched pair, right? You can see that S2 of t is S1 of capital T minus t. All right, so the question is, can we approach this in some non-conventional way? In a conventional way, how would we interpret this? These two signals are not linearly. You cannot express one as the other. This is not one-dimensional signal. These two are linearly independent. So what we can do is we can extract the basis. Is there a slick basis that we can extract here? That's what I'm wondering. Let's just do Gram-Schmidt orthogonalization. Let's say psi 1 is going to be S1 of t divided by square root of energy 1. What's the energy of this signal? So it's energy 1 is going to be integral from 0 to t, a squared t squared divided by t squared dt. So this is a squared over t squared, t cubed over 3 from 0 to t. So this is a squared t cubed over 3 t squared. So it's a squared t over 3, if I did everything correctly. So psi 1 of t becomes S1 of t divided by this. So this is a t over capital T divided by square root of energy, a squared t over 3. So a and a cancels. and we end up with, let's see here. This is t over, so t over 3t over 3, 2. That makes sense. If I square this and integrate from 0 to t squared over here. Okay. So that's my psi 1 of t. So t psi 1 of t looks like this. And this, when this is equal to t, that's t over 3. So this is going to be 1 over 3 square root of. It seems like 3 needs to be above, right? Right?
Yeah.
So it goes square root of 3 here. Right? So this is when t is equal to capital T, then this is square root of 3t. What? Right?
Oh, yes.
Right? When I substitute t equal to capital T, then I have this is t to the 2 over 2 minus 3 over 2, so I'm left with t 1/2 downstairs. So it's square root of 3 over t. Now I need to take the dot product between these two and then get another basis vector. So let's do that.
Excuse me, Professor.
Uh-huh.
Why now it's the way of we solve Gram-Schmidt orthogonalization is kind of like different rather than before. I mean, like before that, we find the E1 and Psi1, and
It's
we
not
compare.
different. I'm doing it exactly the same. And this is the first one. Now I'm going to do second one by projecting the second vector on the first one and then normalizing what is left out. It's exactly the same way. What am I doing different?
I mean, like the dot product of the like S2.
We're not yet to the dot product. We just took the first one and normalized.
Okay.
Right? So now we're going to take the dot product between first and the second one, subtract that, and then normalize that.
Yeah, substitute and normalize.
Right? So let's take a dot product between S2 of t and psi 1 of t. Right? That's what we need to do. Go ahead.
He's just asking for the structure of the optimal receiver. We still need to do the Gram-Schmidt.
Well,
Wouldn't it just be a match filter for each of those?
well, you can do that, but here's the problem with it. These two are not orthogonal. So you can do that. I don't know if that would be optimal receiver. If you just match these two, then you're projecting over non-orthogonal vectors, right?
So is the match filter only optimal when they're orthogonal?
I think so. Yeah, you have to make them orthogonal. That's a good question. Might not. That would be one way of doing it. I don't know if it's.
For the correlator type, you need to do this.
The traditional way how you would approach this is just what I'm following, right? But I haven't set enough to kind of think, can I do this slightly different, right? But traditionally what you would do, you would find an orthogonal basis, express these two as orthogonal basis, and then correlate, just end up doing the same thing. One way to do this, as you're suggesting, and that kind of makes sense, but I have to do the whole thing to see if that will work. Find the mesh filter for this, find the mesh filter for that. But the thing is, what you need to be cognizant of is, here's what the suggestion is. Let me just this is H1 of t, and this would be H2 of t. Now, if you were to do H1 of t matched filter to S1, would that essentially be, let's say, matched to S1 is equal to S2 of t. And then H2 of t, which is matched to S2, would be S1 of t. Now you see what happens in this case. You end up here, let's say when S1 is sent, S1 of t is sent. Let's see, 1, and this is 2. What do you get at output 1? At output 1, you get 2 epsilon s over n0, right? Now, at output 2, you get an autocorrelation of the signal with itself. So you're going to get, you know, you're going to get essentially at the output 2, you're going to get y2 equal to, so S1 is sent, and this is S2, so you're going to get S1 of t convolved with S2 of t, right? That's what, no, sorry, S2 of t convolved with itself. No, sorry. S1 convolved with S1. Right?
H1 convolved with H1.
Because H2 is equal to S1
S1.
of t. Right, so if you send S1, here you're going to get the output match filter, and here you're going to get S1 of t plus S1 of t, convolved with S1 of t, and S1 of t, and N of t, convolved with S1 of t. And then here, when S2 is sent, then here you're going to get Y1 is equal to S2 of t convolved with S2 of t plus N of t convolved with S2 of t, and you're going to get 2 epsilon s over N0. Right, so I'm not sure if you can, now you can calculate these two and see what it is, but I'm not sure it's optimal, right? Because you're not, you may actually get substantial values here, you know, in the opposite branch. But if you do what I just started doing, we already showed that this is an optimal way. You just have you orthogonal basis, and then you have 2 orthogonal filters, and that's the best you can do. You know, that's our correlating receiver.
Why do we need to have a convolution on this step? We don't need to have a convolution.
Because the output of the filter is the convolution of the input and impulse response of the filter.
Is that match filter?
Any filter.
For anything?
But when we do the correlation, we didn't necessarily end up with a match filter. When we went
Say again?
And now the correlation.
The correlation, just because we do correlation won't produce a match filter, will it? Because when we did the proofs during the lecture, we ended up with the match filter as being the optimal.
Correct. The optimal for maximizing signal to noise ratio in the branch, right? But the question is, what happens in the other branch?
If they're not orthogonal.
And if they're not orthogonal, you may get the substantial value there.
Yeah.
And then can this? I need to go and look at can this shift over the decision bound? And my hunch is no, but you know, I'm kind of playing it safe this way. And this has to work. Go ahead.
Did you get N of t? From where? N of t, is that from the
That's the node.
from the node?
AWG.
Oh, okay.
That's the structure, right?
Yeah, yeah. Nice.
But I'm not sure it's optimal, right? We have to do math. Did you do it? Did you try it?
So you're going the route of a correlator?
I'm going the route that we kind of demonstrated in class that is optimal, right? I'm actually, I realize these two are not orthogonal. So I'm gonna say, well, let me extract the orthogonal basis set. And I started by first one, got the first vector, I'm gonna get the other one, which is orthogonal. And then I'm gonna say the first is this, the second is gonna be, you know, expressed in terms of two other orthogonal vectors. And then I'm gonna, then I'm done, because I know that the output of each one of them is square root of 2 epsilon s over n0. And I already calculated, because this ends up being two-dimensional signaling, for which I know that probability of error is q over square root of s and I. So I'm done as soon as I decompose this into two orthogonal vectors. Right? And I know that this is an optimal way. It cannot be better than that. Now the question is there an alternative? And this needs to be validated. I see this is something that would kind of jump at you as possibility, right? But what I will do is complete this, get what the boundary is for optimal performance, and then do this and see if they're the same. Because I'm not sure it's the same. I don't think it's the same. Right? You understand what I'm, why am I saying that?
Yeah, you're saying some of the energy from the other signal would
Show up here,
show
right?
up there.
And then the question is whether presence of this energy can put me over the decision boundary. Because here you have the vectors
But Dr. K,
that,
even if
are like this, right?
even if we have our, when we use our correlating, we have orthogonal filters.
Yeah, when you do correlating, you have this, right? And you're signaling with these points.
But if you ran,
So your decision boundary is like,
or we would be saying in S2, one of them is going to be showing up in both of them anyway, because they're not orthogonal.
yeah. Well, you just have to do the work. I mean, it's understandable what needs to be done. It's just it takes some time. It will be interesting to determine if this would be just as good as what I'm trying to do.
Take it away for a fun.
Hmm?
Take one for final.
But did you do it? Did anybody? So why do I give the homework problem? So I can do that.
Adaptive filters is really
But that's the process. You have psi1, then you determine psi2, and then you're essentially signaling by over these two vectors, and then you have the decision boundaries that are. You have two vectors, psi1, and psi2, and this is your psi1. Your decision boundary looks like this, and you're signaling, you know, with 2 points that you pick in there. Go ahead.
Well, this is actually a basic question. How can you say like the signal, in the beginning you said that the signal is not orthogonal, so where we can see that?
The dot product of these two is not equal to 0.
It's not zero?
Yeah.
Dot product of that one is not zero?
No. Do you see that?
some component. Somebody.
Oh,
Well, for starters, you see that both of them have DC values.
yeah, DC value.
So when you have two signals that have DC values, the product will have a DC value. And then integral over something that has a DC value has to be different than 0. All right, so let me think a little bit more about it. I don't know if that's try these two approaches. Try doing psi 1, psi 2, and then for that we have everything solved in a class. And then try comparing that against these two and see if you get the same result. Let me go over some of the problems, because these are obviously a little bit hard for the exam. So let me go and do some problems that are of the difficulty that's appropriate for exam. says, it says consider a transmission of the binary pump. So this is the binary pulse amplitude modulated signal over AWGN that has N0 over 2 equal to 10 to the minus 10 watts per hertz. The transmitted signal energy is EB is equal to A squared T over 2, where T is the bit interval and A is the signal amplitude. Determine the signal amplitude to have, so desired probability of error is equal to 10 to the minus 6. And the data, so determine A so that probability of error is met. If part A data rate is 10 kilobits per second, part B is 100 kilobits per second, and part C is 1 megabit per second. All right, so let's look at what we're talking about here. So you have your binary fan. This is your N of T. Signaling, we have here our matched filter, and here's where we have probability of error. Now, for binary pen, probability of error is given as what? As, what did we say, Q over square root of 2 epsilon s over n0. Right, so that's, and we want this to be 10 to the minus 6. Now, epsilon s, in the case of binary pen, is the same as EB. Why? Because the symbol, there's 1 bit per symbol here, right? And in our case, this is given as A squared T over 2. That's what's given. So, if probability of error is equal to 10 to the, so it becomes Q over square root of 2 times A squared T over 2 divided by N0. And this has to be equal to T to the minus 6. So now we have everything. We have Q table that will allow us to determine what should be this argument so that the value is 10 to the minus 6. If you go to the Q table, you can calculate that this argument, which is square root of A squared T over N0, needs to be equal to 4.8. In other words, Q of 4.8 is approximately 10 to the minus 6. Okay? So now, A squared times T over 2 divided by N0 over 2 is equal to 4.8 squared, which is 23.04. Or A squared is equal to 23.04 times N0 over 2 divided by T over 2. And A is equal to square root of 23.04 times N0 over 2 divided by T over 2. Now, for different data rates, we know that T is equal to 1 over Rs, where Rs is the symbol rate, right? We're signaling over the interval that's duration T, so the symbol rate is 1 over T. But since this is a binary pulse amplitude modulation, this is 1 over RT. So now if I substitute the values for part A, I guess T is equal to 1 over 10 kilobits per second, 10 times 10 to the 3 in seconds, so this is 0.1 millisecond. I get that A is equal to 23.04 times 10 to the minus 10 divided by 0.1 times 10 to the minus 3. This gives you 0.0048 volts. And then part B, you get T, which is 0.01 millisecond, and A is equal to 0.0153 volts. And then part C, you get that T is equal to 0.001 second, and A is equal to 0.0484 volts. What is the message here? The message here is kind of embedded in this equation here, that the probability of error depends on the energy of your symbol, or energy of your symbol. So if you're making your symbols shorter, which means you're increasing your bit rate, you have to make them taller so that the area under the square of the curve remains the same. And that's what's happening here. As you make your symbols shorter, your amplitude needs to go up so that the energy stays the same. And this is our familiar concept, coming even from the Shannon's theorem. It says if you want to signal with a higher rate to maintain the same probability of error, you have to increase your power, maintain your energy per bit to total noise ratio. Okay.
Sir, I think you mentioned divided by 2.
Where?
Square.
Oh, probably.
Is
Probably, yes. Just
T by 2.
yeah.
so this should be over square root of 2, right? Let's take a look at another problem. Okay, so this one is easy.
Easy.
Why A divided by square root of 2?
Because that's from
I
the
forgot, actually I need to multiply, right? Because I forgot to divide by 2 here.
Oh, okay.
It should be actually times square root of 2. Because this square root climbs upstairs.
the question is why it's 4. Oh yeah.
All right, so let's switch to number 2. Consider a 4 PSK and 8 PSK signal constellation shown in the diagram. So I have 2 PSK modulation schemes. One is 8 PSK and the other one is 4 PSK. So this is psi 1, psi 2, psi 1, and this is psi 2. I have 4 symbols here. And I have 8 symbols here. And then this is the distance between 2 adjacent symbols, D, and this is D. Let's call this D8 and D4. It says here, determine R1 and R2. This is R1, this is R2. Determine an R1 and R2 such that the distance between 2 adjacent points is in the 2 constellation is D, so it's the same. From this result, determine additional transmitted energy required in 8 PSK to APSK signal to achieve the same probability of error as in 4 PSK. So what should be R1 relative to R2 so that D4 is equal to D8? So determine R1 relative to R2 so that D4 is equal to D8. Why are we requiring D4 to be equal to D8? We saw that the probability of error is dependent on the distance, Euclidean distance between adjacent symbols. So if we were to maintain the same probability of error in these modulation schemes, we would have to increase the energy of the constellation in the case of the 8 PSK. So what is D4? D4 is the magnitude of R1 e to the j n 2 pi over 4 minus R1 e to the j n minus 1 2 pi over 4. Just the distance between these 2 points. And it's easy to see from just this drawing that it's R1 square root of 2. Right? That's the distance in a QPSK constellation. D8 I can calculate as R2 e to the j n 2 pi over 8 minus R2 e to the j n minus 1 times 2 pi over 8. Which is equal to, what do I have here? How do I calculate that? I actually write this formally, but then I calculate it directly from this constellation. You can see that this distance here, this is equal to R2 squared plus R2 squared again, minus 2R2 squared times cosine of 2 pi over 8. What is this? This is a cosine theory. Right? Yes. If you have A, B, alpha, C, then what is C squared? It's equal to A squared plus B squared minus 2AB cosine of alpha. Right? This is our cosine theory. So here I have D8 as R2 squared plus R2 squared minus 2R2 times R2 times the cosine of the angle. But what is the cosine of the angle? You have 2 pi divided by 8. Right? So it's 2 pi over 8. And when we do some analysis, so this becomes actually D8, and I have to take the square root of it. Right? So I have 2R squared is common, R2 squared. And then I have 1 minus cosine 2 pi over 8. And then taking the square root of all of that. Where, so this becomes R2. And then 1 minus cosine is sine squared, 2 times sine squared over half angle. Right? So this becomes, I guess, 4 sine squared or pi over 8. Pi over 8. And then taken square root. So this is 2R2 magnitude of sine pi over. That's the when you take the square root, and when you substitute the values, this is 0.7659 times R2. So that's the distance D8 expressed in terms of R2. So now if I take the ratio R1 over R2, R1 over R2 is equal to 0.765 54 over square root of 2, which is 0.5412. So R2 needs to be approximately 2 times larger than R1. Now, if you look at energy, 4 is equal to R1 squared, and energy 8 is equal to R2 squared. In other words, if you look at the PSK constellation, the energy of the symbols, the distance is square root of energy. So the energy is the square of the distance from the origin. So if you now look at energy of 8 over energy of 4, it's going to be essentially 1 over 0.5412 squared. Or if you want to express this as 10 log in dBs, I guess, energy, so 10 log of E8 and E4 is going to be 10 log of this number, 1 over 0.5412, which ends up being 5.33 dB. So you need to increase the energy of constellation by 5 dB to maintain the same probability of error.
Excuse me, should that be 20 log?
Yeah, 20 log.
There.
Let me see if there's anything that we can. Let me do one more real quick. This is the problem number 5. It says consider a digital system with probability of error given by this. Probability of error is given as e to the minus signal to noise ratio. Right, so that's the waterfall curve that's characteristic of this signal. So there's a transmitter, then there's a line, then at the end there's a receiver. Line has a length L, and loss is L equal to 3 dBs per meter. Right, so this is how much I lose when I put the signal into this line. The following data are known. Your transmit power is 1 milliwatt. Your bandwidth that you communicate over is 1 megahertz. The noise figure of your receiver is 7 dB. And power spectral density over noise, which is single-sided in this case, is 4 times 10 to the minus 18 milliwatts per hertz. The question is, determine the sensitivity of receiver and probability of error equal 10 to the minus 6. So probability of error is equal to 10 to the minus 6. Determine receiver sensitivity. What is the receiver sensitivity? It's the signal level that you need to provide at this point so that you meet the target probability of error. So how large the signal to noise ratio at this point needs to be? Well, if your probability of error is equal to e to the, this is in e to the minus SNR linear. If I take the log of both sides, I get that SNR in linear is going to be minus ln of probability of error. Right, so that's the SNR linear. In our case here, signal to noise ratio linear needs to be minus ln 10 to the minus 6, which is 6 ln of 10, which gives me a value of
13.8.
13.8 in linear, right?
Yeah. $24 dB. Please correct me if I'm wrong.
6 times ln of 10.
24 dB, and that
It's 13.8, which SNR in dB is it's 11.4
oh,
dB.
I got wrong.
So that's the signal to noise ratio that needs to be provided here. Now, how strong the signal needs to be in this point? Determine the maximum length of the line. So that's part B.
And
Maximum length
oh,
of the line. Well, what is the power of the noise at this point? Noise is going to be 10 log of KTB plus F in dB, right? Which is going to be equal 10 log of 4 times 10 to the minus 18 milliwatts per hertz times the bandwidth of 10 to the 6 hertz and plus the noise figure of 7 dB. So this gives me minus 107 dB. So that's the power of the noise that is presented to the receiver, taking into account the noise figure of the receiver. So now we know the power of the noise, we know the signal to noise ratio, so how strong the signal needs to be. So the power of the signal at the receiver needs to be power of the noise plus signal to noise ratio. So it's going to be minus 107 dBm plus 11.4 dB and so minus 95.6 dBm. And then what is the path loss that I can sustain?
path loss.
Maximum is going to be whatever is the transmit power in dBm minus the signal at the receiver. Rx dBm. So this ends up being 0 minus 95.6 dBm. So this is 95.6 dB. If I'm losing 3 dB per meter, the length of the line is path loss maximum divided by L, which is 95.6 dB divided by 3. So this is 31.8. Okay. Any questions here? These are typical problems that you encounter, right? You're given with the performance of the receiver, which is given in some sort of your waterfall curve, right? So this is how these curves would look like. That will give you probability of error as a function of SNR. Depending on what kind of coding you have and how much of an error you can correct during your coding, you can actually specify what is the probability of error target that you're trying to achieve. typical numbers is 10 to the minus 6 or even 10 to the minus 9 or 10 to the minus 3, depending on what is the level of cooling that you use and how much you want to distribute the load between the power and the power of the cooling. Based on this target, you actually read your signal-to-noise ratio requirement. Based on that ratio requirement and the noise that you have at this point, which depends on the bandwidth that you communicate and over, and the noise figure of the receiver, you can determine what the signal needs to be at this point, and then you calculate backwards how much the losses can sustain.
That's with wire, right? So whenever it doesn't have any wireless, so we don't need to calculate the bad loss with the 3 dB per meters? Or?
Of course, you know, this here is your channel, right? Channel. Regardless of whether this is wireless or wireline, you have these 2 points. This is your transmitter point, and this is your receiver point. The difference between the power levels and between this point is what we call link budget. This is how much you have to spend. And you can, in this case, I'm spending it on a line. In the case of wireless, I'm going to spend it on a distance. You know, in the case of whatever may be the communication system, I actually calculate the maximum separation between transmitter and receiver through a given medium. And these are relatively easy problems. Where this can change, for example, I can say, here I gave you explicitly the waterfall curve. I might actually put a drawing of it so I kind of, like it's in the most scenarios, because a lot of times, you know, depending on what kind of signal processing you have different waterfall curves, and they may or may not include the coding in them, right? Sometimes we actually simulate with the coding, and you get the waterfall curve that are, you know, a family of curves. It tells you this is the performance with 2/3 convolution encoding, this is the performance with 1/3, you know, and so on, right? You get for different coding levels, and then you can read and get your signal-to-noise ratio requirement based on a particular coding scheme.
Last class we talked about the probability of error. I mean on the PSD. So if we don't have a expression of probability of error. So how do we find it?
You will either given waterfall curves, where I'm going to ask you to read from the curve, right? Or I'm going to say what modulation scheme it is. If I can say something, this is, we're using, let's say, 4-level PSK.
4-level PSK.
Right? And then give you the formula for that one. There will be some Q functions there, maybe 4-level QPSK, right? QPSK, and we have an expression for probability of error in QPSK. Or I can say this is 8-level binary PAM that I'm using, and we have a general expression there where the power is actually embedded in the Q function. So then you go backwards and you look up the Q table and you get what for a given probability of error, what the argument needs to be, and then you calculate what the power needs to be to have that, or actually power over N0 over 2, right? Power of the signal-to-noise ratio, and then from there you can go backwards.
So we use the formula 1 over root square of 2 phi sigma, and then expression that all the formula to find the Q table.
No, but remember we calculated the probability of error in the case of
but the scale for 2 is going to be compared.
in the case of the pulse amplitude modulation, right?
Mm-hmm.
I have it here. Let's say it's on the page 413, right? We have the probability of error in Emery pump is given as 2 times m minus 1 over m cubed square root of 6 times p average times t over m squared minus 1 times m0, right? So that gives you, you know, expression, right? So you can start from there, right? And then if I want this to be 10 to the minus 6, then M is known, so I can calculate what P average times T is over N0, which is your energy per symbol divided by N0.
Right, that's 6.
Or, you know, you can, there's figure 755, where I can actually just give you that figure. And if you look at it, you know, you can read from the figure for a given probability of error. If I say, for example, that you're signaling with a 4-level pump, and desired probability of error is 10 to the minus 6, then you can read from the curve that you need about 15 dB. And then you go from there. And, okay. All right, so I'll post these other problems as well. There's quite a few other problems that I solved. And just do your examples, do, you know, what you did for homework problems, and that's pretty much it. It's going to be 2 hours, because on Thursday, more than a week from today, right? I believe 6 to 8. 6 to 8 on Thursday.
This one?
Not this week, next week.
This room?
This
This week.
What's your next one? Of course.